Okay. Well, good evening, everyone. My name is Sumant Nigam. I'm the chair of the Department of Atmospheric and Oceanic Science and director of the Maryland Mesonet. And James Hyde is a valued colleague in the department. And so I'm very happy to introduce him here. James is the manager of the Maryland Mesonet, which is a statewide network of instrumented towers taking meteorological and hydrological observations to advance emergency preparedness in the state and also to advance the accuracy of regional weather forecast. It collects data every few seconds of a suite of variables, and so it's going to be very important for improved weather prediction moving forward. James grew up not far from here in Anne Arundel County and has been fascinated with weather since he was very young. He pursued his undergraduate studies at Millersville University in Pennsylvania, not very far from here, in part because my department did not have an undergraduate program when he was looking to go to get a degree. His terp bona fides come from his brother, sister, and mother, who are all proud of having gone to University of Maryland. James earned a master's degree in emergency management from North Dakota State University in Fargo, where he studied decision-making in response to hazardous meteorological conditions. He joined the North Dakota Mesonet after completing his master's and became an instrument specialist in short order. He spearheaded their 5-year, $5 million program to build out or to expand the North Dakota Mesonet from 70 plus to 140 plus towers, 75 to 180 towers. James came to Maryland to our department in December of 2023 and has very ably led the development of the Maryland Mesonet. When he arrived, we had only one tower running, and today we are at number 40 in a period of 2 years, thanks to James and his team in sort of erecting this structure. Besides the Mesonet, he's also involved in a number of other department activities. He sort of is the advisor to the UMD Weather Challenge team, which is a national forecasting competition that enhances students' forecasting skills. He advises undergrads on the weather writers team, and also helps people create a weekly forecast video. He's also helping out on the micronet, in building out the micronet, advising students and helping them with instrumentations. And finally, he's an integral part of the Climate Resilience Network, which brings us to today's seminar. James?
Thank you, Sumant. Yeah, long backstory for a short life thus far. So we're going to talk about how we measure weather. So people perceive, feel, get impacted by weather every day, but we're going to talk about how we come to measure it, where we came from, and where we're going next in regards to weather monitoring. So a little bit about what we're going to go through today. We're going to go through how the birth of meteorology came to be, how we developed the instrumentation to measure the weather, how that instrumentation then became indispensable for modern life, and the transition that's happened between going from analog meteorology to digital meteorology in the past 50 years, how that revolution's come about, how we've lost a lot of what we had along the way, and why this modern meteorology in terms of surface sensing is a little bit of a mess. And then we'll talk about where do we go from here, and how everybody has weather problems, and really what's next when it comes to observing meteorology. So, the birth of meteorology. This comes from William Edgar Knowles Milton, this quote, who's one of my favorite authors. He is basically a godfather of instrumentation meteorology in his studies. But he said meteorology as a science can hardly be said to have existed before the barometer and the thermometer. We didn't know how all these things linked together in the atmosphere above us until we had instruments in order to measure them. I will then say that and then disagree with him because he forgot one important thing, which is the rain gauge. Rain is obviously I consider the most important variable for us as humans. It allows our crops to grow. It allows us to gather fresh water from the atmosphere. And so the birth of the rain gauge came in about the 3rd century BCE in India. Not all too surprising because of the monsoon season in India, a very annual pattern that revolves around wet and dry cycles. And so our ancestors were not stupid. They knew that these cycles happened. And so they wanted to figure out, where does it rain and how much over the course of the season. So our first records of surface meteorology come from the Indian subcontinent. This is not the actual text, but it was written in Sanskrit. And they basically had these small containers. We don't know the size of them, but they were called donras. And basically, through verbal communication and written through Sanskrit, they basically said how many of these containers filled up in a particular season, right? The first quantifiable meteorology came from Korea. And so the story goes in 1442, the king, Emperor Sejong the Great, sent each one of these steel, first they were cast iron, then they were copper, bronze, etc., of these buckets to his provincial governors, and he required them to install them in the courtyards. And along with those came with a stick and a rule that every time it rained, the provincial governor himself must go out and put the stick in the bucket to see how much. And they called the measurement on these sticks puns, if I'm saying that right. And we now know, because they still exist, they measure about 0.12 inches or a third of a centimeter. And so here is the last the one we know was used. It was carbon dated back to the 14th century. It exists now in Busan, Korea. Continuous measurements were written from 1442 to 1908 with a period of 466 years. So this was what I call the original mesonet. Tens of these rain gauges throughout Korea, serving the province. So we go to the Enlightenment period in Europe. We've got Galileo and Copernicus, and they're discovering the stars, and they also they're discovering or rediscovering, you might say, what is around us. So the first meteorological instrument was temperature. They noticed that when you heat or cool metals and other things, they expand and contract. And so they wanted an instrument to tell them how much it was going to expand or contract by. So these instruments were usually made of glass, and the expanding contraction was either air and water. So you had a thing, a vacuum effect. The second meteorological instrument was pressure. And this was about 1650. People, philosophers at the time were exploring with things like vacuums and siphons, right? And so they noticed that basically when you turn on a vacuum and you put your hand up near the hose and it sucks it to you, right? They considered that the force of vacuum. Well, now we know that it's actually not the vacuum that's providing the force, it's the outside air pressure that's trying to fill in the space that provides the force. But they needed a sensor to do the same thing. And then the third one, around the same time, it's unknown whether the barometer came first or the hygrometer came first, but these were developed around 1650. So again, this all comes from the book, which I have a copy of. Here are those instruments. So this is an air water thermometer. This is a barometer by Hooke, famous British philosopher. And then over here is my favorite. We have a hygrometer made out of horsehair. Basically, as anybody knows, if they have long hair, whenever it is dry outside, your hair contracts, it goes frizzy, right? And so what they did is they used that same principle. So when the air was dry, the hair strand tightened and it went up on the scale, and when it got wet and it loosened, it went down on the scale. And so they used hair as a humidity sensor. So when the thermometer was introduced, preliminarily, there was, a rush because everybody had to have their own thermometer, right? And so obviously, when you're a philosopher in the 17th century, making to look a name for yourself, you create a thermometer and then you put your own scale on it, right? And so we had every single person who made a thermometer had to have their own scale. So we've got your normal, you got Celsius, Kelvin, Fahrenheit. There's also Rankine. Isaac Newton made his own scale, which was ironically nonlinear, unlike other ones. But basically, and funny thing about Celsius is that Celsius's original scale actually went backwards. He put 0 as the boiling point and then 100 as the freezing point. And then he sent that thermometer off and somebody said, this doesn't make sense. And he flipped the scale around, and that's actually how it today. So this is from XKCD, one of my, if you're a scientist, you know about XKCD probably. He created the cursedness scale, right? So we have Celsius and Kelvin, kind of a 2 out of 10, right? But we have some really weird ones. Isaac Newton defined his 33 as hot as the hottest water you can hold your hand in. Very, very, precise measurement. How hot can you hold it? That's 33, right? And so we have all these different temperature scales all over the place. And it's quite funny. And so we have the classic situation about standards. There are 14 competing standards. That's ridiculous. We need one that covers them all. There are now 15 standards, right? And so that was kind of the early summarization of the early period. By 1750, we had developed the glass blowing technology and other things so that we could actually encapsulate things like mercury, which are much more stable than air, into glass thermometers. So here we have Lord Cavendish's thermometer for high and low temperatures. So we can actually record like what the high and the low is, something we can consider very basic today. But they also became easy enough to create that they got put on ships. And so one of the first meteorological records, actually not from land, we have a lot of records that come from the ocean. So this is a climatological database of the world's oceans from 1750 to 1850. Spanish, Dutch, British, French ships. Every single one of these dots is a meteorological observation taken by a ship. So very, very impressive by the time we, get to the turn of the 18th century. No longer a novelty. So we've gone from, hey, this is a pretty cool thing, to now this is pretty essential to commerce and trade and military applications. And so by 1835, when the telegraph was developed, we can actually send signals back and forth about meteorological observations, right? And so we can start to create maps. And so this map is from 1887. It's a Dutch map, but basically they took a bunch of observations, and now we can actually start to see what looks like surface charts, right? And so by the time we get to World War II, meteorology is no longer a
the first thing you can notice from the is that it's got a lot of observations on German. It's very obvious that we'd already broken the German code. Able to use those in our forecasts. But at this stage, the weather was actually coming from the west, and so we were interested in things that were coming from the Atlantic. Some of these observations were coming from ships, and we know that those ships we had pigeons on board that were flown back to the UK, and those were providing information on weather and not giving away the position of the ships. But we've got a deep area of low pressure down here to the south of Iceland, and this was due to move across the country during the next 24 hours. This would bring strong winds, it would also bring high waves into the English Channel down here, both of which were unsuitable really for the D-Day invasion of northern France. We were drawing up these charts in front of us every 4 hours, and there were meetings quite regularly with the commanders, and the decision was made relatively straightforwardly that the weather on the 5th was going to be too difficult to go.
So the World War II forecast for D-Day is in the meteorological forecasting sphere is often called the most important forecast or the greatest forecast. They delayed the weather, the meteorologists at the UK Met Office delayed the D-Day invasion by 2 days. And there were strict requirements for sea height as well as
how this is supposed to get.
tides, and they had to meet those. If the forecast was wrong, the boats that they went, the landing craft they went ashore would have drowned, the tanks would have gotten stuck on the beaches, and the invasion would have failed. This is where, colloquially, I think we can kind of say that forecasts and meteorology stopped being a science and started being operationally useful for everyday life, military applications, commerce, trade, whatever you have it. This is kind of that turning point. And it also, you know, all the people who went over there expected, oh, they got a forecast right. You start to see trust and confidence in forecasts, that we can actually make real decisions that impact lives based on it, right? And so that was the real turning point. So also around that same time, obviously the mid 20th century was full of rapid technological change, and one of that is, of course, happened in meteorology with the digital revolution. So part of the digital revolution that we have to talk about, and this is where I'll transition from more of a historical to Maryland focused. So as Dr. Prestegard saw in her presentation you saw 2 weeks ago, this is Atlas 14. So this is the stations in Maryland that contributed to the Atlas.
Meteorology started.
And so all of the orange dots here are 1 day recording intervals, and then all the
wait, Maryland.
Right? And so you can see that there's a lot of them, but we can see from this chart that we've since about 1970, we've lost a lot of stations. So the way that this turned out was that when people came home from World War II, they were very, interested in weather, and weather stations were, plentiful. And so that lasted through about 1970, 1980. And then we had kind of the information age, right? We started becoming a services society and less an agricultural society. And so we started to lose these people who would get up every morning and take an observation at 8 a.m., right? And so we started to lose a lot of these daily stations. This analysis, because it uses the Atlas 14 data, only goes to 2000. I know for a fact in Maryland, we only have about 10 to 15 today, right? So this number that was at 70 is down to 15. And number of hourly stations that actually also gone down too. The number of hourly stations we have at ASOS airports, right, are now only about, it's actually gone up a little bit from this graph. It's gone up to about 15 as well. But in total, we've lost. So this is that breakdown of the length of some of these stations. So some of them last through the entire period. Some of them are only 15, 20 years, but you can really see from about 1980 to about 1990 or so, we lose a lot of these sites. What we're also losing is what I call the human touch. So the human touch is people actually going in and physically writing down the observations. So this is an hourly report from Baltimore on February 3rd, 1976, right? And you can see that it's dutifully marked by pencil every single hour with clouds, with weather, with winds, etc., right? And actually what we have now, if I were to look at this chart on an actual thing, it would only give me 3 numbers. The high, the low, the precipitation. That's it. So all this handwritten information, we have lost down to 3 numbers. So we lost the human touch. And this is even more disheartening for me. This is a journal that is in the AOSC archives, in the AOSC library. It was written the one on the one on your right was written in from 1920 to 1921 by James Stewart, and then the one to the right was written. It's kind of hard to see, but it's written between 1908 and 1909. And so we can see here the original handwritten observations every single day for February 1909. None of this is digitized. We've lost this completely. We have it, but it's not in any sort of record that we can evaluate.
Unknown caller.
So we have to digitize it ourselves. And I'll talk about that in a second.
From Harvard
This is
now.
what we have. This is our legacy of weather observations in Maryland.
Hello.
Sitting on a shelf. All these handwritten observations, millions of people hours going into this stuff, and it's just sitting on a shelf. So that's why I say we kind of lost a lot of what we had in this digital transition. And as we know, climate is the average of weather at a place over a period of years, right? So we have a period of years, we have the weather, we can turn this into climate data, but we don't have it, right? We don't have it in a data set that can be able to be used. So let's talk about getting more positive. Let's talk about the analog to digital revolution. So by 1900, instrumentation had become advanced. Industrial revolution, we see springs and watch timer. It's done on clocks now, right? So this is a barograph, right? So it basically plots the barometer is actually this big cylinder on the bottom here, and then it goes to a lever and it puts a piece of ink on a paper, and so it traces a trace, right? So pop quiz time. The date is July 4th, 1956. Does this ring a bell for anybody here?
No.
No? What about this location, Uniontown, Maryland? Does that ring a bell now? Yes. Hold on. we'll let it be a surprise for everybody. But I see a few hands. Okay. Right? This is the worldwide record for 1 minute rainfall. The worldwide record for 1 minute rainfall occurred in Uniontown, Maryland on July 4th, 1956. The hardest it's ever rained in the world in 1 minute. Here, right here in our home state. And this is the barograph. This is the graph that they made that decision on. The one on the right, the one with the 2 lines, that's actually the calibration run. So they couldn't believe that this had happened. So what they did is they took the same instrument and the same piece of paper, and they manually poured water into it with a precise amount to see what it did. And yeah, it came out within like a couple hundredths of an inch. So the question is, why is there a gap in this trace here, right? So it's this flat line, and it goes up, and then it goes up, and the line disappears, and then it starts out. Why do you think that might be? Now I'll take a question from the audience. Anybody know why that might be? Why does the ink disappear? The ink disappears because the needle was moving so quickly that it didn't have time to deposit the ink on the page. We actually don't know. It could be that in 30 seconds, half of this fell or more. It could be 75% fell in 30 seconds. We don't know. But basically, the pen was moving so fast it didn't deposit the ink on the page. So now we have fully digital instrumentation. So this is a picture of our data logger we use for the Mesonet, right? We're taking observations every 3 seconds. Includes rain, temperature, wind, all your basic meteorological variables, right? So now if that same thing happened again, we could actually say with pretty much certainty, yes, it rained this hard in this amount of time, right? If you want to hear more on why that's a problem, go back on YouTube and watch Dr. Prestigard's presentation. So we talked about our instruments, right? And so this is all those instruments, the hygrometer and thermometer specifically, has now gotten down to a package that's 1.5 by 1.5 millimeters wide. And it can sense the temperature up to 0.1 degrees Celsius, 0.2 Fahrenheit, and within 1% relative humidity. This is what we use in our stations, actually. It's this exact sensor, right? NIST traceable, all this stuff. It takes like hardly any power, 0.4 microamps of power. It's insane how far we've come even in the past 10 years. 10 years ago, this would be a chip the size of like a tiny like film slide or something. And now we've got it down to something that you can fit on your fingernail. So I thought this graph would be a cool demonstration of how far we've kind of come. So the miniaturization of instruments coupled with how easy they are to access. In the 1800s, stations were a couple hundred miles apart and they were being taken maybe once a day. right? And so by 1900, we're taking once an hour, and they're 100 miles apart, and now we're here, where this is a log-log plot, obviously, right? So time and minutes on the x-axis, stations and y, right? And so we're kind of in the center. By 2050, we're going to be probably every couple kilometers in every 1 minute or less. We're already starting to do that, right? So we've really accelerated this analog to digital transition. I call this section everything and nothing at once. So this is a little animation I took from Weather Underground. So these are all backyard stations that are feeding into, Weather Underground or NOAA or, what have it may be, right? So look at all these stations. They're hundreds of them, right? And I get closer and closer in. This is Montgomery County because they have a little bit of a denser pocket. You basically go street by street and you can tell what the temperature is, right? We have all this data, right? So we have everything now. But there's a problem. Here's a backyard station. Looks pretty nice. This is what I would call a very nice station. It's out in the middle. There's no trees. The radiation shield where the temperature is being measured is about 5 feet off the ground. That's pretty good. And then you can see in the background here that this person has an anemometer up on top of their roof away from, the roof line, and it's about, 10 meters up. This is a good station, right? I would trust the data that came from the station. I would actually prefer it was aspirated radiation shield, but this is a good quality site. What about this one? Okay. The rain's probably going to be pretty good. I don't see a wind. So is that, if this station is reporting wind, is it 0 because there's no sensor? Or is it 0 because, it's just reporting 0 because it's off somewhere else? We don't know, right? It's underneath some gravel and some rocks. It's kind of low. It's maybe only like 3 feet high. It's unaspirated, right? You'd say, maybe you take the rain from the station, but you wouldn't take the temperature. What about this one? Is there anything useful really providing? Yeah, probably rainfall, right? But this person has his thermometer, which is the little gill-looking thing, right next to the roof. That roof is baking. It's just going to produce hot sunshine, right? And the wind is blocked. It's below the roof line, right? So I wouldn't trust the data from the station. Maybe you could count rainfall, right? And then we have this kind of stuff, right? The rain gauge is blocked. You can't do anything with this, right? But yet all of these stations are reporting to Weather Underground, but there's no pictures. We have no history of it, right? Which do you trust? If I go back to here, right, and we look at this map and I say 4 of those are the 4 stations you saw on this map, tell me which one, you'd be hard pressed to find, right? So we have everything, but in a sense, nothing. It's garbage in, garbage out. This doesn't go for backyard stations. To belabor the point even more, these are our DOT highway stations. This one's pretty good. This one is on 695. I drive by this all the time. I've driven by all of these, actually. Okay, that's decent. What are we doing? Really? Right? So this is being fed into the models, into the National Weather Service, and they're supposed to make life-critical decisions based on a station that's 20 feet away from 40-foot high trees. We got a problem. This one's next to a rock pile. I'm sure the temperature's great. And these are our national climate sites. These are ASOS sites, right? These are at, I'll give you a guess which one this is, but you can kind of see that this little thing in the center, that's where the instruments are, and it's covered by a concrete pad. Now it's surrounded by grass, but it's under concrete, right? Does anybody want to guess which one this is? It's DCA. We are surrounded not only by concrete, but in the larger context, an airport with active runways, with jet exhaust exceeding 1500 degrees Celsius, a huge body of water, and an urban environment. Is this a great place to take climate data? Arguably not. And yet, this is what the entire record for the area is based off of. Here's another airport you might be familiar with. This is, as you can see, also on gravel and concrete, right? But grass surrounding it. This is BWI. And you can see, actually, so what's funny, this apron, this cargo area to the south, or on the page here, this was just put in the last 10 years, and the area that you can see under construction up there is brand new. So not only are we, kind of destroying the local meteorological environment, but we're adding to it, right? And there's even more expansion plans in this area. Yeah. So we have all these stations and all these observations, but I created a little word cloud here, pun intended, of what are we doing? We have sensor, we have metadata problems. Are they aspirated? Are they calibrated? What's underneath them? Surface reference, maintenance, cleaning. Do we have pictures of them? All this stuff we don't know, right? So we're making all these educated guesses based on this data that we really don't have any idea of what's going on. So this is also another cartoon. So whenever I see one of those little weather stations, I have to fight the urge to climb up and spin the ammonometer real fast to make sure to think it's in a tornado, right? The one at the bottom says, pour one out for precipitation data integrity as you upend the glass into the gauge, right? Yeah, so we have these problems, right? Okay, so what are we gonna do about it? Where are we going with this, right? So you may have heard of something called the Maryland Mesonet, right? So the Maryland Mesonet, as Sumant said, is a statewide distributed network of professional scientific grade weather stations that we're deploying throughout the state in a pretty equal pattern to enhance emergency preparedness and commerce, but also critically for this talk, they are properly sited, calibrated, maintained on a season by season basis, right? And we have records that make sure, and we have quality control. So if this were to happen, where the spinny thing, this would actually get caught by our QA/QC controls, right? Somebody went to one of our rain gauges and dumped a whole load of water in, that would be caught by QA/QC, right? Because it says, that's near impossible. And then a human would have to look at it and say, is it possible? Is it not? Was there a thunderstorm overhead? Make the adjustments, right? Yeah. So what are we measuring? We're measuring temperature, dew point, wind speed, sunshine and clouds, right, through a pyranometer. New is we're doing soil moisture and temperature. So this is kind of a new frontier that, meteorologists, and people who deal with the atmosphere are starting to become like, wow, actually surface flux and evapotranspiration is really important to our, not only our surface hydrology, but also like how the atmosphere interplays with the earth and the boundary layer, right? So this has become more critical. So this is like a new data set, like soil moisture and temperature pre-2000, let's say, was not even a concern. Soil temperature and moisture was for the soil scientists and the agriculture, not for meteorology, but we've since learned our ways. Rainfall, snow depth, right? Snow depth's always a hard one. If you ever look at our snowfall maps on the website, sometimes they show ridiculous values. It's just because there's no good way to measure snow depth rather than just sticking a ruler in the ground. We actually still need humans for that. A little bit about the Maryland, really about the Maryland Mesonet background. So from 2018, 2020, UMD and MDEM, conjoined on this idea. In 2022, there was $4 million allocated to the project, right? 2024, the first stations were installed. Today, we're at 39, 40, it'll be 40 probably by the end of the year, stations. And then, we expect full build out, 3 per county, approximately 75 by like in mid-end of 2027 at this point, right? So we're more than halfway. So the goal of the Maryland Mesonet is to continue the legacy of the people who took the original observations and wrote them down, right? So we are trusted continuous data monitors because we live here, we're measuring the community, we're doing, testing, calibrating, accuracy. We have long-term support, right? So there's no real hit and run science going on, right? It's not like we come in for a research project and then we do our science, we publish a couple papers and we're gone, right? No, we're here for the long haul. We measure with the weather today to monitor tomorrow, right? Not only for forecasting, but also for climate and other things, right? And then we're designed to give real-time data-driven solutions for weather problems. And everybody has weather problems, right? One of the things that I like to say is that, weather impacts everybody. Weather doesn't care about what social class you're in, how much money you make, your politics, whatever. It's going to, impact you, right? And so there's lots of areas that weather impacts, from environment, agriculture, you can read the list, water use, emergency management, utilities, construction, media, all this stuff, right? So everybody has a weather problem, right? So how do we turn those weather problems, how do we solve those weather problems, right? Well, first we need the infrastructure. That's where we are right now. We're developing infrastructure. We turn that infrastructure into data, right? We then use that data to create tools like maps and things that will be useful for these industries, right? We then turn those tools into products and services, right? I put Mike's climate impact dashboard up here, right, as a potential product that we're collaborating with, right? And then do those things get into services? And finally, well, we need these things to continue. We want these stations to be in for a long time. So how do we make that happen? Can we turn those data products and services operationalize them into assets that then pay dividends back to the original infrastructure, right? So it's this feedback loop, right? Use the infrastructure to create the products and services and the data, which then feeds the infrastructure, and then you kind of get this positive feedback cycle, right? So wrapping up here, we'll go into what's next. So here's what we're working on in the future, what we want to do, right? In terms of meteorology for Maryland. We're working on data visualizations and summaries, so turning all of the data into climate statistics. So here's the summer of 2025, right? Departures, for example. By the way, this was produced by Alfredo Ruiz-Diaz, and he's Maryland State climatologist who works in our department and works closely with the Mesonet. Data aggregation and integration. It's so, coming back to Maryland, it's so fun and exciting to learn what other kinds of meteorological tools there are out there just in the region. There's so much science that goes on, but we don't often use that scientific information. We use it for research, but we don't operationalize it, right? So one of my goals is to actually operationalize some of these things, right? So on the left here, I have, this is a plot that I created called an RDQVP. It's a radar based plot, and basically take radar with height. And so what this shows was the snow event that happened. This was the snow, not snow event that happened earlier in the month that schools got delayed for 2 hours for, right? But it just rained the whole time. Had we had this at the time and operationalized it, we could have seen that the melting layer at 3 kilometers was there the whole time. It was going to be rain from the absolute onset, right? And so this was, we knew the rain, the melting layer was above us at about 7 UTC, right? That's 4:30 in the morning. If we had known that information, distributed it to the school systems and said, hey, there's already a melting layer above us. It's very, very likely going to be rain when it starts, right? Could we have saved that 2-hour delay? Could we have saved, the morning commute mess that happened, right? On the right, we have, so this is Maryland Department of Environment, has a bunch of different things, LIDARs and celiometers. This is their SODAR. A SODAR is a wind profiler, and this is great for severe weather, but also with forecasting, right? So what I've done is I've basically taken their wind profile and created a photograph out of it, right? And so we can plot these in real time and show them on the website, and then give that over to the Weather Service, who can make decisions based on those things, right? We're also exploring the possibility of micronets and specialty networks. So we are currently in the process of entering an agreement with Montgomery County to take the sites that we have from the Maryland Mesonet and then expand them in the county so that they have tighter coverage within the county, right? So there's the sites that are currently in are Lay Hill, Potomac, and Poolesville. There's potential to add 3 to 4 more, right? And Montgomery County is kind of the furthest we're along with, but there's other counties. I got an email today with a unnamed county that wanted to collaborate with us on doing these kinds of networks. if anybody remembers the big flood that happened in May in Western Maryland in the Western Port area, Charles Creek, yeah, that was bad. And the reason was partly because they don't have any, there is no weather stations in that watershed. None. So what are we gonna, we've been approached by MDEM and the county to say, can we do something about this? Can we put in a little bit of a network so that, if there is heavy rain in the upstream part of the valley, we can alert Western Port downstream that, hey, your library is going to be flooded and you get the kids out of the school, right? This was a very interesting article I came across in Nature. This got sent to me about a machine learning, AI if you want to call it, tool that reads old handwriting and is specifically trained to notice weather words, right? And so these people have developed it in Europe, and they're making it open source. So basically you can scan the image. So this is the image that I had before. Can we take this book and then, instead of having somebody who knows how to read 19th century handwriting in order to do it ourselves, right? And have it be transcribed. Can we turn that into a data set, right? Yeah. Ultimately, I want to take all these books and transcribe them. We're also reducing the cost, right? So one of the key barriers to entry for good data is getting good data out of low-cost sensors. So we know the sensors are low cost, but aspirated shields are essentially that forces air through the shield in order to adequately bring the sensor to ambient temperature. They can reduce biases by 2 degrees Celsius. And so what we're doing is, this is a senior currently, Katie Lehman, who's working on this project for the Maryland Mesonet. To buy one of these sensors off the shelf, commercial off the shelf products, between $500 and $2,000 to buy one of these things, right? If we 3D print it, and here you can see her model, right, with the fan and the shield and whatever, our prototype is currently running between $45 and $50. We are literally order of magnituding, quality, good, accurate data for temperature, right? If any one of those backyard weather stations that we had earlier had one of these, we could be a lot more trustful in the data, right? So, also, we're training and teaching the next generation of observers, right? I'm proud to say that we've had a number of interns, thanks to Climate Resilience Network and the funding provided by them, go through and learn about all these things, right? So about rain gauges, about timber, how quality control and QA/QC is so important, and what makes a good weather station and what makes it accurate, and the pitfalls that you have with data in the modern era, right? So we're really training the next generation of observers. I thought this was a kind of a cool dichotomy between summertime and us freezing our butts off in Garrett County. But yeah, and with that, that's our goals. So I'll take any questions.
I'm going to give you the online question.
I turned on the speakers in the room. So.
Oh, I didn't know you could do that. Thanks, James. So for our Q&A, we have plenty of time. So does anyone in person have any questions? There's a question. Oh, there's a question.
Hi, Joel. There. You didn't know about the SODAR plot, did you?
No, I appreciate you showing that. Can you hear me okay?
I can.
Thanks for showing that. This is awesome, educational. I want to borrow that book you mentioned too.
I have it. I'll loan it to you next time I see you.
Awesome. Just like an FYI for talk about legacy and measurements. Really appreciate you showing the radar wind profile there again. But an FYI, those things are approaching end of life completely. That the technology is no longer being supported. So something I guess this region is going to have to discuss is whether or not they're useful to continue, or whether we should adopt some other, like a LiDAR system or something like that. MDE can't afford brand new systems, so that's something we have to talk about.
Well, part of my goal, Joel, this is out in the public, but part of my goal to operationalize those things is to make sure that people can use them and they are useful, so that we can get the funding to rebuild them or supplement them or replace them.
I'm all about it. Get a radiometer or something out there. Get moisture profile also. That'd be awesome. But yeah, or just an FYI, I guess, for the community.
Yeah.
Maybe estimate maybe 2 to 5 years. They'll be obsolete.
I'll send you the script.
Awesome. Thank you.
Yep.
Questions? I have a question.
Sure. Go,
I was
Kezzy.
just giving everyone else an opportunity. This is like less of a meteorological question and perhaps a biology one. When you're talking about the old humidity tool that uses horsehair, why did they choose horsehair?
So horsehair was the most common because it was the most plentiful. But when I was reading the book, they used human, horse, and beard hair. Beard hair was actually very effective.
Why?
Beards.
But why was it most effective?
I don't know. It just was.
But the distinction between
I challenge
beard
anybody who
hair-
has a long beard, go and try it. Do your own science. But people had long beards back then. So I guess they just trimmed it and twirled it up and then made a hygrometer out of it.
beard hair as opposed to human hair, like those were two different.
It also depends on the thickness and the porosity of the hair.
Yeah, it depends on like the keratin gel. Yeah.
Okay, good answer, good answer.
Human hair used for certain humidity. Okay.
Can I have another question?
Kind of hair they want.
Okay, let's get back to meteorology.
Yeah, I enjoy very much. Nice talk. I wonder what is the minimum? You were talking about station densities and the plan to expand it in Montgomery County. I wonder what is the best spot in densities? Like modelers, how much they can live with, or
So this is a question that's going to have to be. It's a good question. As far as the economics go, you do pass a point of diminished returns, right? So it's basically a logarithmic slope that basically, we think you don't get much benefit beyond like 5 kilometers or so. The network that we're developing for Montgomery County is about 6, right? There are specialty cases where if you have a unique situation, such as a valley or something similar that has steep inversions or something, then that could be useful. But the way we do the mesonet is actually we try to make it as representative for the surrounding terrain as possible. And for places that aren't that way, like perfect example is the western part of Maryland. We have the ridge and valley region, right? So it's these, tall ridges going into these steep valleys. What we try to do is we try to stagger the stations so that one is on a ridge, one is in the valley, one is on a ridge, one is in the valley. So you can and then we have some in between. We try to really average it out so we can say, okay, the station that's on this ridge or near this ridge is probably representative of other ridges in the area. Right? And the thing that happens in this valley is probably representative of other valleys in this area, right? But yeah, you start running into diminishing returns between 1 and 5 kilometers. There's the kind of, techno bros out there that want to put a sensor on every single leaf of every single plant. And that's inspirational, but probably not going to move much data. In my agri-meteorology background, when I worked for North Dakota, we found a lot of success. We had stations 20 miles apart, but because it was so flat and uniform out there, we found very, very consistent readings in that area. So it really depends on topography, but really, if you're averaging it out between ridges and valleys and stuff, 5-ish kilometers. As far as modeling goes, that's not my forte. You probably have to talk to somebody in AOSC, maybe John Potterjoy for that, about what kind of is the most efficient in terms of density. But there's obviously a cost. If you want to, there's kind of an inverse relationship between data quality and number of stations you have, right? Because you're trying to maintain a great quality for 1,000 stations, you're not going to be able to keep up with them, right? So.
Joel has his hand up again. Joel, you can go ahead.
Joel, you're muted.
Oh, I couldn't hear if that was me or not.
Yeah, you go.
The follow up on that micronet for these communities, the air quality realm is also going that direction where more and more communities are asking for these micro scale measurements. I wonder if there's an opportunity to collaborate on like a multi-scale in a multi-scale way. I guess my thought process is the microscale meteorology you bring to community could even help identify localized neighborhood flows and show which fireplace is fumigating the entire neighborhood for one. But then you could upscale it. I wonder if there's opportunity for like microphysics studies.
The great thing about the way that we designed the Mesonet, Joel, is that the towers that we have now, as you can see on the screen, these are skeletons, right? So we started with the bare essentials. Let's get humidity, let's get temperature, let's get rain, let's get wind, right? But there's nothing preventing us in the future from going the direction of air quality or biology or whatever. I had a call with an emergency manager last week saying they wanted radiological measurements on the tower because they are downwind of a nuclear power plant, right? And so if it were ever to have a bad day, then they could do that. So, but the great thing about the Mesonet is that we've expanded capacity in order to accommodate those needs. Now, as far as tracking a chimney down, Tim probably has much more experience, but there's people here, and obviously you know where to find me, and there's other more knowledgeable people here than me to answer those questions. Yeah, go.
Just to expand on that, we put a micronet station over in the chemistry building with a black carbon monitor to measure black carbon from the buses in front of Regents because they're all going to get electrified soon. And so we're getting this baseline before, after they're electrified. Hopefully we'll have the after and see a significant decrease in black carbon emissions.
Yeah, and those are those specialty applications where, there's kind of, one of the things that's I kind of want to do, and I've touched a little bit on this, is that you can do meteorology when you're doing research, right? You can have these stations and this equipment feeding valuable data back to the decision makers, even when you're doing research with them, right? So,
any other questions, online or in person?
Yeah.
So this is a comment on resolution. So the models, the state-of-the-art models that provide perhaps the most accurate forecasts worldwide are now running at sub 10 kilometer resolution. And a lot of benefit or a lot of the forecast skill, a lot of it comes from initializing these models with observations, but a lot of it also comes from resolving the lower boundary, the land surface, the terrain, the lakes, the water bodies. So it's important to capture a little larger scale features of the meteorological flow and then use the model to downscale in some sense, dynamically see how they interact with local physiographic features. And that's very helpful. So to get fine scale weather, it's not necessary to get fine scale observations. That's the point I was trying to make, because there is a logical end to, as James said, there's a point of diminishing return here. Yes, thank you.
Yeah, so even if we were run a 1 kilometer model in Maryland, which, is perfectly doable with today's modern computers, right? As long as we, the model makes initialization based on the data, right? And then it knows the terrain, it knows what's going on above it, and then it can kind of say, okay, well, if this is happening here, it basically creates a guess and then gets checked by the observation, right? And so it's self-correcting, right? At least for the first, a few time steps, right? But then it, goes and forecasts forward, yeah. But you don't need one station per box. You just need one that's representative of an area. Yeah.
Any other questions? Online? Okay. Well then,
Louis with the
go
last
ahead,
minute.
Louis.
Yeah, it was a great talk, and I certainly learned a lot the historical aspects. Thought it was really nicely done. China had some temperature measurements and climate that went back 500, 600 years too. That
Yeah.
was pretty remarkable when they were being discussed in the mid 70s as they opened back up. But the one thing I question you on, your question is with respect to that rain event the other week.
Yes.
You know, the local forecast office had a release, you know, from the 0Z release, knew it was going to be rain. The issue was that what was the ground temperature? What was the ground temperature going to be when that rain started? That was the big unknown. And my talking to some of the Weather Service people was that that wasn't as well known as you might think. Okay. So that's point number one. And so when they have their early morning car calls with all the school districts and all that, the Weather Service doesn't make these decisions for 2-hour delays.
No.
Those are made obviously by superintendents and all that, and they have to do their own risk mitigation. And the issue was the uncertainty with respect to whether before sunrise, you know, because those buses go out early, you know, before sunrise now with the late sunrise, whether there would be some areas in which the streets would have ice on them. So, you know, that's a tough call. But by the night before, it was an all rain forecast. And so it wasn't, hey, people were still hungering down for snow. That was gone. And I thought I would just mention that because you do have ground measurements here on this network, and those roadside networks are supposed to help out too on that. And I was disappointed to see some of the sighting as you showed. So anyway,
Yeah.
Those are tough calls. I just want to emphasize those are not meteorological people making those decisions.
No. Well,
Yeah, okay.
One of the goals of the Mesonet, Louis, is to get data in the hands of the decision makers who need it, right?
Yes.
And so,
yes, that's
right, can
all of
we send the, you know, we have ground temperature measurements at 2, 4, 8 inches, and they were all showing that morning of like 40 degrees. I think if those decision makers or those school districts had seen that map, they would have said, oh, well, I think we're probably okay. The road sensors are really good for doing roads. They actually do a really good job. The in-road sensors at those sites are really good. But as far as meteorological, same thing with the airports. You know, the airport sensors are there to provide information for planes. So if the wind and the pressure, barometric pressure is, you know, for the altimeter is right, then, you know, that's kind of all they need. Maybe temperature or freezing rain, you know, freezing rain detectors. But all the other stuff as far as...
It was below freezing at sunset and around here in Howard County. And the superintendents are not going to send buses out until after sunrise in those situations.
Right.
So they're going to do 2-hour delay.
Yeah.
They're not going to take the chance. They're not going to take the chance.
Yeah. The goal is not to make the decisions for them. The goal is to give them the data.
So that's the point. That's the point.
Yep.
These decision processes are really critical. You've got really important information, but people will make decisions that you'll scratch your head over all the time. So welcome to my world.
We can give them all the data in the world, but we can't stop them from making the wrong decision. Right.
Okay.
I appreciate it, Louis. Thanks.
Okay, well, that pretty much brings us at our time. So thanks everyone for attending, but biggest thanks to James for giving us this talk. Great. And this is our last Climate Resilience Network seminar as well, but I hope to see all of you at our conference in just over a month. It's called Scientists Serving Communities. Ask me more.
Thank you.
Oh, where'd the mouse go?
It's right there. I stuffed it behind.